So essentially, I want to give you an idea of how easy it is to get started using HyperDex, show some of the things you can do with it, and show you how easy it is to start with a development cluster and just scale up from there. So here you can see I have my terminal. I've already installed HyperDex. If you go to hyperdex.org, you can actually find the download instructions. And it's usually just apt-get install HyperDex or yum install HyperDex if you're using a Red Hat distribution. So I'm not going to cover that here. But once you have HyperDex installed, it's really easy to start a HyperDex cluster. So a HyperDex cluster really consists of two pieces. You have a coordinator that acts as a shepherd for the cluster. It dictates the state of the system and which way the system should move as it moves through state transitions. And you have a daemon that actually stores the data. And the way the cluster is brought up, you start a coordinator, and I'm going to start it in the foreground. And I'm going to listen on my localhost address. Generally, you'll listen on an external IP, but I'm using localhost for the demo. And I mistyped foreground. So now we have a coordinator running. And so this coordinator is maintaining the entire state for the cluster. It knows every node that's in the system, and it's passing that information out to other nodes in the system. So when I want to start, where am I? Okay. So let's make a data directory. So if I want to start a HyperDex daemon, the only thing I have to do for a HyperDex daemon is actually tell it where that coordinator is. So I'm going to specify that the coordinator is at our local connection, or our local IP. And I can start that up. And I'm going to tell it where to listen because it needs that. So now we have a HyperDex daemon running. So this is the simplest cluster you can have. It's one coordinator, one daemon. The daemon is going to store all the data. The coordinator is going to manage the daemon and serve as an introduction point for clients. And of course, we can start up a Python shell and connect to this cluster. So we're going to go through a really simple example here. I'm going to go through the social network example as or a phone book example is the easiest thing to go through. And if you were watching the HyperDex talk yesterday, it's the exact same hyperspace that you saw then, but in code instead of in pictures. So let's create an admin to talk to the HyperDex cluster. And this is just a connection to the cluster. And we're going to we just pass the address of the coordinator. So unlike many systems, the only thing you need for a client or an admin to connect to the cluster is information about one of the coordinators. So you can contact the coordinator, and everything else is taken care of behind the scenes. The client library figures out where the other nodes in the system are, figures out how to connect to all the other pieces of the system, and it does this automatically behind the scenes in a very robust manner. So now we have an admin, and we can add a space. And this is going to create a hyperspace for a phone book. So we want to call it space phone book. We're going to have a key that's the username. We're going to have some attributes. And I'm going to specify that the phone number is an integer, not a string. We're going to create a subspace, and this is the three-dimensional space that you saw yesterday. We're going to create 8 partitions, although generally the default is fine. It creates 64 partitions by default. And lastly, we're going to specify that we want this space to tolerate 2 failures. And that last line is crucial. It means that at any time we could lose 2 machines in the cluster and not lose any data and not lose any availability. HyperDex will stay operational. You can still make queries against the cluster as long as at most 2 machines for a particular data item fail at a time. Obviously, if everything goes offline, there's nothing anybody can do about that. But HyperDex will remain available for up to 2 failures. So now that we've created our cluster, we can create a client to connect to the cluster. And the reason the client and the admin are separate is just because you want to separate the metadata management from the actual data management. So I'm going to import the client library, create a client, and this looks just like creating an admin. And once again, you only need to specify the address of one coordinator to bring the system into the cluster, or the coordinator in this case, because we only have one. And now that we've got a client, we can actually do things like put, where we just want to insert someone named John Smith into the phone book space. And he's got a first name, John, last name of Smith, and he's got a phone number Let's say he's in the 607 area code and he's got a 255 number. And so it helps if you have valid syntax. So where's the error? Oh, right there. Okay, so we just stored John Smith in the cluster. And of course, we can get that exact same object back by doing a GET request. And so this is the same exact object we just stored. In HyperDex, you're guaranteed that when you do a GET, you will see the result of the latest put. There's no eventual here. There's no eventual consistency where it might be the freshest object. It might be an object you haven't seen for a really long time. It's the latest object. And that's really important, as we'll see later in the demo. We can also add a few more objects to the cluster. Or we can perform searches and add a few more objects. So let's add another person named Smith. Let's make Jane Smith. And Jane's got a different username and a different phone number. Let's put her somewhere out in California. So there we've got Jane Smith out in San Francisco. And then we can do a search. So let's find everybody with the last name Smith. And we want to find where the last name is Smith. It's really hard to see the keyboard or the screen with the bright lights in your eyes, so I apologize for all the typos. So this just returns a list. You can see we've got both John and Jane Smith. And what this search did behind the scenes is it constructed a hyperplane in the hyperspace, the three-dimensional hyperspace. And that plane goes right along the Smith axis. And so when you perform this search, you're only contacting the servers that intersect that plane. In this case, we only have one server, so it's always going to contact that server. But if we had, say, 100 servers in a cluster, it would contact probably a quarter of them, maybe even less, for this particular search. And we can make a more specific search. Maybe we want everyone with the name John Smith. And this is going to correspond to just a line segment in the three-dimensional space. And so it only returns the John Smith object. And we can go further and find everybody with the phone number. Let's say we want everybody with the phone number in the range everybody in the 607 area code. So that's everybody in Ithaca. And of course it returns John. If we wanted to find everybody in a smaller range, it's going to return nothing, as you would expect. So that's the basis of HyperDex. You can put, you can get, and you can search. But many applications need a lot more than just put, get, and search in order to be effective. You want to be able to store maybe a rich data structure. So HyperDex actually offers a number of data types that you can use. So using the same cluster, I'm going to create a new space. In this space, I'm just going to make a list. And in this list, we will store a number of friends. Or actually, let's make it a set. So we're implementing something like Facebook. We want to have the set of a user's friends. So we're going to go back to the admin. We're going to create a space. And we're going to call it profiles. And we have, once again, a username key. And we're going to have first name and last name like we had before. Now we're going to have a set of strings, and that's just going to be the friends. Let's also add another field here for profile views. And here I'm just going to skip over the tolerate 2 failures. By default, it's going to tolerate 1 failure. And okay, I've got a bad space description. Where did I? Space profiles. Ah. It's much easier when the demo is pre-recorded, but that's not as fun. So the typo I made here is that I used the plural of strings for the friends object. So we want a set of strings. We want to get rid of that comma. There we go. We've created the space. And so with this space, we can do things like add to the set. So we can do, first we're going to create a profile for John Smith, our prototypical user. And we're going to give him his first name. And right now he's a lonely guy. He's got no friends and nobody's viewed his profile. So we're going to just leave those as the default. They're going to be empty. And so if someone were to visit John's profile, the system could make a increment to the profile views page so that you can keep track of the number of profile views as a counter. And one way you could do this is you could do a get of the John Smith profile, increment that value, and then write that value back. But of course, we work with distributed systems and big data. It's likely that two people might visit John's profile at the same time, and one of those page views would be lost. So that this doesn't happen, HyperDex provides atomic operations such as atomic add. So we can actually go to John Smith's profile and go to the profile views, and we can just add one view to his profile. And so if we get that profile, you can see that he's got one profile view. We can add again. We're going to have two profile views. And you can just keep doing this until you hit the extent of a signed 64-bit integer. So he can have quite a lot of people view his profile. And I don't think any celebrity on Earth will ever overflow that. Now, after people have started viewing John's profile, they may want to become friends with John. Once again, HyperDex provides atomic operations that make this dead simple. So we can do a set add on John's profile. And we're going to add it to the set of friends. Let's say that Bob or John is friends with someone named Bob. So now we've just added Bob to the set of John's friends. And you can see that it shows up in the set. And once again, all of these operations are atomic. So we could have everybody in this room try to friend John at the same time, and everybody would be added to the set atomically. Nobody's update would be lost. And then when I retrieve John's profile at the very end, do you have a question? Okay. When I retrieve John's profile at the very end, I would see every operation at the same time. HyperDex supports a number of other operations. Let's say that John Smith got married, wants to append his wife's name to his name. We can do that with a string append. I don't know how many people in this room use Facebook, but a lot of my Facebook friends like to randomly just change their last name. So they just append stuff to it all the time. So let's add to his last name. We're going to make him Smith Doe. So now when we get the profile, we can see that his name has indeed changed. HyperDex in total supports about 63 atomic operations, and it's constantly growing. So you can do things like store a map, maybe from friends to the number of times the friends have viewed the profile, maybe from people to the number of things that they like. And you can actually do atomic operations on the values of the map as well. One of the neat things about HyperDex that HyperDex was one of the first NoSQL stores to have is the ability to perform asynchronous operations. So it's not free to establish a connection to a cluster of any type. There's always at least the setup overhead of TCP or the overhead of maintaining your own UDP algorithm to retransmit stuff. HyperDex enables you to reuse these resources to get the most out of your cluster. And the way it does that is it supports atomic operations. So instead of getting John's profile like that, I can actually do an asynchronous get. So here, D is a deferred object. And what this deferred object means is that I can, at a later time, request the result of that operation. And so I could actually pipeline hundreds or thousands or even millions of operations on this single client instance. It will reuse the same connections to the cluster and enable me to, at a later point in time, wait for the result of that instance. In fact, the implementation of Git that I've been using this whole presentation is simply the 2 lines that I just showed you now. It quite literally performs the asynchronous operation and then waits for it to complete. So asynchronous operations are really easy to use, and they're the native operations within HyperDex. And you can do an asynchronous atomic add if you want. You can do an asynchronous get, asynchronous put. So they're everywhere, and they're very easy to use. And with languages such as Go or Node, it actually integrates with the runtime of the language, enabling you to do things like run many Go routines using the same client concurrently. Or in Node, it integrates with the event loop so that you can just write your callbacks like you would normally do. And it just works. It's really great. So let's move on to the next part. So the next thing I want to talk a little bit about is documents. So HyperDex supports JSON documents. This is a new feature. We haven't actually advertised it all that much. We should. So you can take a JSON object and just throw it into HyperDex, and you can do searches over the JSON object. So let's create another space. What do we want to call the space? Let's remove the profile space. And let's recreate the profile space, but we'll do it differently this time. Instead of having a complicated profile, let's just say we're going to have a document that we call profile. And that's the entirety of the space. So working with documents is really easy. Let's say we have a document that looks something like, name is John Smith. So we can do c.put. We can just store this new document for John Smith. And here we just do, and we'll just put H in there. And this HyperDex.client.document just does the JSON serialization of the document and tells HyperDex that it's an actual JSON object instead of a string. With languages like Node, where documents are generally more prevalent, you don't have to do that. The conversion is done automatically. And so we can put this document, and then we can get the same profile that we got back before. And we can see that there is indeed the document name. And you can also add indices to documents. Now, I'm not going to do that here. It's in the documentation. It's a more advanced feature. But you could say index the field foo.bar.name. And then HyperDex will create an index on that field of documents. Any document that has that field, it will index. And we'll do this on a per space basis. So you could say foo.bar.name in the profiles space. And that makes it really efficient to do a search for anything that's foo.bar.name within a document. And you can use any of the search predicates that we have within HyperDex. I showed earlier a range search. So you could, for instance, do a range search over a field, or you could do an inequality search. You can even do a range search over strings. You want everything between X and Z in the alphabet. You can do that. So finally, I'm going to talk a little bit about a new feature that is in the upcoming release of HyperDex. We're actually putting it together in the coming week, but it's available on GitHub right now if you're a little adventurous. And that's macaroons. We provide support for a new authentication primitive from Google. The basic idea of a macaroon is it's like a cookie. Who here has heard of a cookie? Okay, we don't have any web programmers here. So a cookie is just a token that you can pass back and forth. And the problem with a cookie is if I give a cookie to someone else, they now have all the privileges I have. So if you think about a service like mint.com or anything like that, I don't really want to give them access to my bank account. I don't want to hand over my bank account password. So I can't use a service like that because the password is super user privileges for my entire account. Well, macaroons support the notion of a caveat. I can create a macaroon for my bank and add the caveat that only read operations are permitted when that macaroon is presented. And the bank can validate this and enforce those caveats. And the person I give the macaroon to cannot actually remove the caveats. It's cryptographically hard. So macaroons enable this cheap, fast way of doing authorization in a distributed system. And we support macaroons in HyperDex on a per object basis. So that means if we were to implement like a Facebook profile, you could actually have my Facebook profile protected by a password. And only people who have that password with me can access that profile. But I can grant read access to my profile to my friends. I can give them the macaroon to access the profile, and then they can in turn read the profile. But because it's read-only, none of them can actually modify my profile because I didn't give them permission to. So once again, we're going to remove the space. We're going to import macaroons, and we're going to add another space. In this example, let's go with a bank account example. That makes a little bit more sense in this context. It's a simpler example to follow. So we're going to create a bank account that's just got the account number as the key. We're going to give it a name. The name really doesn't matter for the sake of this example, but every account has to have a name. It's going to have a balance associated with it. And then we're going to say that this space is created with authorization. Once again, bad space description. So there we've created the space. We already have our client. And the whole idea of a macaroon is you take a secret, and this secret is like a shibboleth. If I know the secret, and I can speak the secret, I can create a macaroon that authorizes access to whatever object is protected by that secret. So here, let's create a super secret phrase, and if you can copy that, then you have the same access to the macaroon that I do, but we're just going to refer to it as secret. It's just random data. You'd probably just read from dev random instead of pounding on your keyboard. Then we're going to create an account. Let's say is the account number. And then we can just create the account. We're going to use the account number as the key. We're going to say the name is once again John Smith. He seems to be the most popular guy in the room right now. And we're going to say he has $10. He must be a college student. And then we're going to specify the secret. And once again, that secret is whatever secret we created above. And so we've just created that account. And although the secret is displayed on screen, imagine nobody in this room knows the secret. So they can't actually go to the cluster and present the secret to it. So if you were to try to do a get on the cluster right now, what you're actually going to see is that that get operation is not authorized. You can't actually get the object back because you don't have the secret. So creating the token to get the object back is pretty simple. We create a macaroon. So we're saying that the macaroon is just the account number. That's the location of the macaroon, and that doesn't really matter. It's just a string that gives a hint as to what the macaroon is for. We specify the secret, and it's important that we specify the actual secret we provided. It's used as part of an HMAC tree or it's used for the cryptography, and if it's off by even a byte, it's going to not work. Then we can specify some public identifier. And the public ID doesn't really matter. I'm just going to leave it empty for now. So we have the macaroon, and we can create a token out of this macaroon. This token is just a bunch of text. So right now, that token is like the super user. If I gave anybody in this room that token, they could use it to read and update the account. So we can do a get operation. So if we do a get with the token, it works. If we take out the token, it fails. So that token provides some sort of access. And so far, everything I've shown you is just like a cookie. You could steal that cookie off the wire, and you could impersonate me with it. If I gave you the cookie, you have every credential that I have. So let's take a step back and actually create a macaroon that enables, so we're going to create a new macaroon. I'm just going to create it from the existing one. We're going to add a caveat. And a caveat in a macaroon is just a predicate that holds true at the time of the request. If the predicate holds true, the request is authorized. If it doesn't hold true, the request is denied as being unauthorized. So with our first party caveat is that the op is a read. Once again, if I could see, I could catch these typos. So We then create the token out of it. And you'll notice that this token is a little bit different from the one before. It's a little bit longer. And this token, if I were to give it to anyone in this room, only authorizes a read. You can only read from my bank account. You can't actually update it. So if we were to try and get the bank account balance, specify the token, it works. But if we were to try and do something like take away from the bank account balance and take John's last $10, we can't actually do that because it's denied. So the token actually encodes the information that you're only allowed to read the bank account. So no matter what you do, you can't compromise the front-end web server. So imagine like Gmail, there's 1,000 servers out there. Some of them are talking to Bigtable to get your data in the background. If everything is operating on macaroons, then the macaroons are enforced all the way back to the Bigtable layer, or in this case, HyperDex. Even compromising the front-end web server doesn't give you access to the entire database. The only thing you can actually compromise is the macaroons you can get access to, which is only the users who are concurrently using the compromised web server. And we can go further than this. We can add additional caveats that are time limited. So if we were to add a caveat that says this token is only valid for 30 seconds or a minute, it would actually mean that the token is only valid for 30 seconds. So if the attacker gets it, they can only do 30 seconds worth of damage with that token before they have to recapture the token from the client. And so they can only really do a limited amount of damage with macaroons, and that's, once again, enforced all the way back to the storage. So let's add so we're using Unix timestamps here. So let's say that this expires in maybe let's say a minute. So and then we can do that get that we did before. Did that take too long to write it, or? Oh, I tried to do the atomic sub. That was already. So we can do the get. And now I'm going to talk for 30 seconds. And that while I'm talking, that token is going to expire. It's going to become invalid, which means that you can use the token now, but 30 seconds from now, which is going to happen right about now, let's keep watching. It's going to eventually become invalid and not going to work. And when it becomes invalid and doesn't work, that token is forever dead. We added the caveat that it was only valid 30 seconds into the future, maybe 60 seconds into the future. And that means that once it's dead, there's no way to reverse the cryptography and get back to the token without the caveat. And there's no way to force a new token that doesn't have that restriction on it. You can only add restrictions when you possess the token. And so it's impossible for an adversary to go into a state where they can no longer access the objects. And so you can imagine plenty of possibilities with this, right? You can use the tokens to do user profiles. So you can store the password as the secret, and you could authorize access to a Facebook profile using the macaroons. And then you can provide time-limited access to someone else to view your profile. Maybe you send them a friend request that expires in 30 days. After 30 days, they can't use that token anymore because you put an expiration on it. But the true power of macaroons comes from the way they enable distributed systems to work together. I've only shown you first-party caveats so far. The other type of caveat a macaroon supports is a third-party caveat. And a third-party caveat basically says, trust this other service over there to enforce this predicate. So, for instance, I could say, trust that Robert has authenticated with Facebook.com, and if Robert can present a proof from Facebook that he is indeed Robert, this macaroon will accept that proof. And so HyperDex knows nothing about Facebook, knows nothing about, say, LDAP or Twitter or anything else you could authenticate against. But HyperDex can actually use authentication mechanisms like that just by adding third-party caveats that enforce them. So the basis of a third-party caveat is you essentially have two pieces. First, you have to add the caveat to the macaroon. And so I'm going to show you how you do that. So we have an add caveat function. You can imagine that this would actually be implement it as like an RPC service, but for the sake of time, I'm just going to pretend it's an RPC service and just use a Python function. So we're going to generate some unique key for this caveat, and it's important that that key be unique to the caveat. So once again, I'm just going to bash on my keyboard and get something random, but you should use .random. And then we can go to the caveat or the third-party service and say, give me a identifier that says this must be Robert, and this is the password that Robert must provide. So now we have an identifier. And what we can do is we can say, let's create a new macaroon. And once again, we're going to say that this is for the account number. And we're using a secret that we provided earlier that's associated with the bank account. And we can add a caveat that says it's read-only. And then we can add a third-party caveat now that says there's some auth service somewhere in the world that knows about this key and gave us this identifier for that key. And then we can get the token. Once again, this token is going to look completely different from all the other tokens. So we've got that. And now we can try to do a get with that token. So it's unauthorized. And why is it unauthorized? Because there's a caveat there that I have no proof is satisfied. It says I must be robert@hyperdex.org. But there's no proof I'm robert@hyperdex.org. I just said, trust me, I am. And that's not good enough. We need to have someone prove that I am indeed robert@hyperdex.org. And the way we do that is by generating a discharge macaroon. So I will go back to the service, and I will ask the service, give me a discharge macaroon that says I am robert@hyperdex.org. And so we're going to do that. So once again, I'm implementing this as if it's a function, but you would do this as a service. So this service is going to create a new macaroon. The location doesn't matter. It's going to use the key that we provided earlier when we added the caveat. Got it. Thank you. We're going to create that. And then we're just going to return that macaroon. Nope. Okay, there we go. So let's hope that this works. We're going to go d equals and we're going to pass in the identifier, my email address, and the password. Where's the R that I'm missing? Oh, okay. It's very hard to see with these lights, so I gotta do this again. No, it returned none. It wasn't fine. Okay, so now when we call this, we get D, which is a macaroon. And so now we can do the discharge token equals m.prepare for request, d.serialize. So this gives us a discharge token. If we provide both tokens together, we will have the complete proof that I am indeed Robert at hyperdex.org. And so we can get the account balance. And if you don't provide that discharge token, it fails. So the key idea here is that you're able to delegate the act of checking these caveats to a third-party service. So natively, HyperDex will integrate with any authentication backend you have. It'll integrate with your LDAP server, it'll integrate with your Exchange server, and it all does that natively thanks to the power of macaroons. The HyperDex server is completely unaware these other services exist, and yet via fast cryptographic operations can have a hard guarantee that you are indeed authenticating as who you want to authenticate as. So the macaroons are really enabling a new set of applications that, combined with HyperDex's strong atomic operations and asynchronous operations, are not available on any other NoSQL store. And with that, I will be happy to take questions.
Okay, so do we have any questions for Robert? Any questions at all? We'd like to thank you then, Robert, for your workshop.